Everyone, so in this video we're going to explore the map function in Haskell. So the first thing that I'm doing here is I'm asking Haskell what is the type, what's the type signature associated with the map function. So by running :t there, by running :t here on my shell and passing in the map function, Haskell tells me that the type signature with the map function. So over here, the way you interpret this is that the type signature with the map function is the following. The first argument, the first input into the map function over here is basically a function. It takes in a function, and the second argument over here is a list of A's, and then finally as an output you get back over here a list of B's. Now keep in mind that there's no constraint associated with the B, with an A, and with the A and the B in this function there, which means that A and B could be anything. A in theory could be a number. It could be a char, a character. It could be a list of something. It could be a function, and you get the idea. It could be anything. It could even be a list of something else. It just could be anything. And likewise, the same applies. The same applies even for B. Okay, so now given this kind of the understanding behind the type signature, what I would like to do is, without using the inbuilt map function, let's just go ahead and create our own version of the map function. So what I'm going to do is, on my other shell over here, I'm just going to change directory into 324, and let's just create a directory here. I don't know, YouTube videos. Let's go inside YouTube videos, and let's just create a file called, I guess, my my map.hs. Okay, so really straightforward implementation here. I'm going to use the non-tail recursion implementation, and I highly recommend you that, after you're finished watching this video, you may just want to re-implement the map method, the map function, using the tail recursion version of it. So coming back over here, let's just put some code together for the map, and I'm going to say, so let me just zoom in a little bit so this becomes a little bit more clean for everybody. Uh, okay, that should be good. And so let's call our own version of map with a map prime. So I'm saying map, a single quote there. And the first thing, what map does, I know from the type signature, that map is a function that takes in as a first parameter some kind of a function, and the second parameter over here is some kind of a list there. So let's do that. Let's provide our two argument set. This over here is my argument one, and this piece over here is my argument 2. So I need to somehow create a placeholder here for argument 1, put a space, put a placeholder for argument 2, and then equals to something, but the something is going to be over here. That's my output. That's this piece over here. This piece over here is my output. So let's use that idea and put this implementation together. So I'm going to say map prime, where if the first parameter is some kind of function, and let's have a variable f that is going to hold that function f, and I'm going to use pattern matching that, if the second parameter is basically an empty list, then the output is going to be an empty list there. Okay, and so again, as a recap, this entire piece over there basically is inside that. F is a function that has the following type signature, and if my second argument, which is this list of A's, if this list of A's happens to be actually empty, right, then my output over here, the output over here is basically, which needs to be a list of B's, that's going to be empty as well. Okay, so that's by just using type signature, I put the first line of my implementation together. Now, if I say map prime, and if my first argument is still some kind of function f, using pattern matching, if I have a list of A's there, But by using pattern matching, remember what I've essentially done here is that if we assume that this list of A's, let's just assume that this list of A's happens to be 1, 2, 3, 4, meaning it's basically a list of integers there. Okay. Via pattern matching, x in this case refers to x in this case just refers to the integer 1, and xs refers to the actual list of integers, which is 2, 3, 4. Okay, and that's what the pattern matching does. Using the cons operator, this over here is the cons operator. Okay, so just review some of the material from lecture 2 just to get an understanding for what's happening here. But what is essentially done is it has basically taken this structure and it has kind of decomposed it into its two subsequent entities, where the first entity, this x over here, is basically just the integer itself, and this piece over here is a list of integers. And because it's a list of integers, the convention, or at least the kind of the style that folks use in Haskell, is that this is a plural version, meaning it has many such x's, so we use xs there just to for us convenience sake, that and make the code a little bit more kind of in some sense readable, that this is a plural version of x and this is a singularity version of x there. Okay, so this is the case. If this is the case for my two arguments, then the output over here needs to be some kind of a list of p's. Remember, the entire map function when it takes in the argument 1 and argument 2, it gives you back a list of p's. That's the output there. And how do I get that list of p's there in this placeholder? Okay, so if I already have a function f that basically goes from a to b, okay, what I can really do is take my first x, okay, and this x over here is basically has a type. The type associated with x is just a, and the type associated with xs is basically a list of a. Okay, this is something that I already know from my type signature there. Okay, so if I already have a value of type a, and that value happens to be inside the variable x there, if I apply the function f on x, what do I get back? What kind of a value? What I get back some value, but what's the type associated with that value? The type associated with that value is basically just b. Now, why is this the case? Because if my function goes from a to a b, if that's my function f, and on that function f, if I pass in any value of type a, okay, that happens to be x there. X contains some value that happens to have a type a associated with it. Applying that function on that value of type a, I get back some other value that happens to be of type b. So the entire type associated with f of x is basically b. The type associated just with f is basically a function that goes from a to b, and the type associated just with x there is basically some value of type a. Okay, so if I've got f of x there, okay, that happens to be of some value of type b, then this placeholder that I'm trying to get completed there, this implementation could look like one could be f of x, and then just put it in a square bracket there. And guess what? This completely obeys the type signature. F of x happens to be of type b, but the moment I put them in the square bracket, so the type associated with this piece there is basically a list of b's. So is this one kind of a value? Is this entire thing? Does this entire thing obey the type signature of this piece there? The answer is yes, it does. It completely obeys a type signature. But if you think about this, I'm not even using XS anywhere in my implementation. So what I really need to do is need to think about a little bit of my code here, because I have some kind of an implementation there, but it's really not the implementation of what map essentially does. Okay, I somehow still need to use XS there. So I'm going to continue with the non-tail recursion version of this implementation, and I'm going to say this is going to be equal to f of x. Okay, that happens to be some kind of a list of b's, and I'm going to just concatenate this with the remainder of applying map prime on xs. which means if I call map prime again, map prime on f of xs, what's going to happen here is there are a few interesting things that you can note here. We already know that the type associated with this piece there is basically a list of pieces. We already know the type there. We also know the type of this piece, this entire piece is going to be what's the type of this entire piece there? Well, it's right from there. If map takes in argument 1 and argument 2, it gives you back something that happens to be a list of pieces. So if map prime takes in my argument 1 and it takes an argument 2, the entire piece of this box over here is going to be some kind of a list of pieces. Okay, now what's the type associated with this plus plus? The type associated with the plus plus is basically a string concatenation where I take in some kind of a list of something. Okay, so let's say this is a list of B's there, and it takes in a list of B's and it gives you back a list of B's. That's what the plus plus operator does. It's basically it's basically a list concatenation in Haskell. So what's the first argument to plus plus? The first argument to plus plus is basically in this case this list of B's there. Do I have a list of B's? I do. That's the argument right there. F of x in the square bracket notation is my list of B's. I got my first argument right there. So let's check mark that. Plus plus needs as a second argument another list of B's there. Do I have another list of B's? I do. This piece over here, this black box there happens to be some value that happens to have a type of list of B's. So I'm good with this piece too. I've got my first argument, I've got my second argument. So now on plus plus, if I pass in my first argument and I pass in my second argument, what do I get back? Well, I get back something that happens to be a list of B's. What is that list of B's? This entire piece in red, over here. Okay, this entire piece in red over here happens to be a list of B's. This entire piece in red is the output, that you get back from the map prime function by applying the first argument and the second argument. And that's exactly what we're trying to do here. We're trying to get back a list of B's by applying map, by passing in the first argument and by passing in the second argument. Okay, so now let's just try this out. Let's just make sure that the code is correct. So this is Vim. So I'm just going to save my code there, come back to my shell, and I just need to make sure where exactly I'm on my file system. So that's the path there. I'm going to take that path, come back to my shell, and I'm just going to load the entire thing, which happens to contain the file mymap.hs. Okay, so I'm just loading my code on Haskell, and if everything is okay, you should see the message okay module loaded, and now I can just try my code out. Before trying my code out, let's just see what the inbuilt version of the map function does. So the inbuilt function of map, if I pass in +2 and I pass in some list of integers, it gives me back a list of B's there where +2 has been applied on every single one of these numbers. Okay, so 4 plus 2 is 6. That's where I get a 6 from. 5 plus 2 is 7. 6 plus 2 is 8, and 7 plus 2 is 9. This is the inbuilt version. Okay, and now I'm just going to run our version of my map, and let's just open the code as well. So let's just open our code there. Okay, our version is called map prime. So now I'm going to do the same thing, but now I'm just going to replace the map with a map prime, and we'll see that we get back the same answer. So and that's exactly what you're doing here. We have a function +2, we have a list of some A's there, and we get back a list of B's there. Okay, so just to put some nice colors there, this entire piece in black is basically associated with our +2, and this entire piece, let's say in orange, which happens to be a list of A's, that list of A's is right there in that orange there. And then I have a list of B's there, and this list of B's is basically over there. Okay, now of course these types A and B's could be completely identical. Okay, So when I see a B there, when I see an A there, it doesn't mean that this list of B's has to be something that has to be different from the type A. It could be different. It could even be completely identical. Okay, so keep that in mind there. And so those are my boxes there. And if you look at my lecture slides, you're going to see the entire kind of the recursion that has been traced out for one such example. Okay, so I highly recommend you watching, at least looking at my lecture slides to get that work through of the recursion.